The Soviet missions to Venus are not what you think. Almost everyone pictures Venus as just a hot, dead rock next to Earth. But something happened here, and no spacecraft has entered this atmosphere since the Soviets. That is about to change. NASA is building a probe, a titanium sphere designed to be dropped straight through the clouds of Venus. It will search for something scientists have been arguing about for decades. The mission is called DAVINCI. So, let's dive in. The name DAVINCI stands for Deep Atmosphere Venus Investigation of Noble Gases, Chemistry, and Imaging. It is also a deliberate tribute to Leonardo da Vinci, the Renaissance artist and inventor whose spirit of innovation and relentless curiosity the mission is designed to embody. Because, as the project's principal investigator has explained, the mission is meant to bring the art of science and technology to Venus. That principal investigator is Dr. James Garvin from NASA's Goddard Space Flight Center in Greenbelt, Maryland. Dr. Garvin has spent years describing Venus as an enigmatic sister planet, and his central question is deceptively simple. Why does Venus not look like Earth? DAVINCI was first proposed as a mission concept back in 2015 as part of NASA's Discovery program, a series of lower-cost, focused planetary science missions. It was selected as one of 5 finalists, but in 2017 it lost out to 2 other missions, Lucy and Psyche. The team revised the proposal, sharpened it, resubmitted it under the name DAVINCI Plus, and in June 2021, NASA selected it as one of its next Discovery-class missions. Alongside Veritas, another Venus mission focused on surface mapping from orbit. The mission is tentatively scheduled to launch in June 2029 and arrive at Venus to begin its atmospheric descent in June 2031. It is built around 2 primary components. The first is a spacecraft called CRIS, which stands for Carrier, Relay, and Imaging Spacecraft. CRIS is the vehicle that carries the probe on its journey to Venus, performs scientific observations during multiple flybys of the planet, releases the probe into the atmosphere, and then serves as a communication relay to transmit all of the probe's data back to Earth. The second component is the probe itself, a titanium sphere about 1 meter in diameter, packed with 5 scientific instruments inside a pressure vessel. This is the part that will be dropped through the clouds, through the acid, through the heat, and into the unknown. Dr. Garvin has compared it to a deep ocean submersible, the kind used to explore famous shipwrecks like the Titanic. Except instead of water, this submersible is diving through an ocean of carbon dioxide. Venus, he says, has an ocean of air to explore. The conditions inside that atmosphere, the density, the pressure, the way the probe drifts through it are more like deep ocean exploration than anything resembling a traditional space landing. The deeper you go, the thicker and hotter it gets. And the probe must survive all of it. Before the probe ever touches the Venusian atmosphere, CRIS has a long and carefully choreographed journey ahead of it. DAVINCI will make use of 3 separate gravity assists from Venus itself. These are maneuvers that use the planet's gravity to adjust the speed and trajectory of the spacecraft without burning precious fuel. Each gravity assist serves a specific and deliberate purpose in the overall mission plan. The first flyby of Venus occurs approximately 6.5 months after launch. During this pass, and during the second flyby that follows, CRIS performs remote sensing of the planet. It studies the cloud tops in ultraviolet light using an instrument called the Compact Ultraviolet to Visible Imaging Spectrometer, or QVIS. This instrument investigates mysterious compounds in the upper atmosphere that absorb ultraviolet light, compounds whose exact identity we still do not know. On the night side, another instrument called the Venus Imaging System for Observational Reconnaissance, or VISA, senses heat emerging from beneath the clouds to study the composition of the geological highlands below. VISA also studies clouds on the day side in ultraviolet, producing cloud motion movies that track atmospheric dynamics. During these flybys alone, the spacecraft acquires over 60 gigabits of new data about the atmosphere and surface. One detail about Venus that differs wildly from Earth and adds a layer of complexity to the mission. A single day on Venus, the time it takes the planet to complete one full rotation, lasts 243 Earth days, longer, in fact, than a Venusian year. The planet rotates backwards compared to most other planets in the solar system, and it does so extraordinarily slowly. That means the night side of Venus is an incredibly long, unbroken stretch of darkness. After the second flyby, Chris spends roughly 2 more years positioning itself for the main event. It takes that long to get the geometry right. The third and final gravity assist puts the spacecraft on its final approach, aligning everything so that the probe can be released directly over the target site, under ideal lighting conditions at high noon, with the sun directly overhead to provide the best possible illumination for the descent cameras. That target site is a place called Alpha Regio, and it is one of the most extraordinary and least understood features on the surface of Venus. Alpha Regio is a highland region, a kind of rugged, elevated plateau, roughly twice the size of Texas. Its terrain is classified as a tessera, a type of geological formation that, so far, has only been found on Venus, nowhere else in the solar system. Tesserae are strange, wrinkled, deeply ridged landforms that scientists do not fully understand. They cover about 8% of the Venusian surface, and they are believed to be among the oldest terrain on the planet, potentially billions of years old. Some scientists think they may be remnants of ancient continents, the geological bones of a world that may once have looked very different from the hellscape it is today. If Venus ever had plate tectonics, if it ever had liquid water flowing across its surface, if any process resembling what shaped the continents of Earth ever occurred there, the evidence might be preserved in these ancient rocks. That is what makes Alpha Regio so valuable. It is like a geological time capsule, and DAVINCI is going to open it. But here is the critical gap. No spacecraft has ever studied or photographed a tessera up close. Of all the international missions that descended through Venus's atmosphere between 1966 and 1985, not a single one targeted these highland formations. They were discovered using radar instruments, mapped roughly from orbit, and then left alone. DAVINCI will be the first mission to closely explore Alpha Regio, and the probe will not just measure atmospheric gases on the way down, it will photograph the mountains. It will take the first close-up images of a tessera ever captured by any spacecraft from any nation. The last photographs ever taken of the Venusian surface came from the Soviet Venera 14 lander back in 1982. That was more than 40 years ago. DAVINCI will return the first new surface images of Venus since then. Now, here is where it gets intense. Approximately 2 days before reaching Venus, the CRIS spacecraft releases the probe flight system. Encased inside the protective heat shield, spinning at about 5 rotations per minute for stability, is the titanium descent sphere. The probe begins to interact with the Venus upper atmosphere at about 75 miles, or 120 kilometers, above the surface. At this altitude, the probe is moving extremely fast. The entry velocity is approximately 10.4 kilometers per second, and it enters the atmosphere at a relatively shallow angle of about negative 6.3 degrees. That shallow entry angle is deliberate. It is much gentler than the Pioneer Venus probes used in 1978, which came in at a steep angle of nearly 34 degrees. The shallower angle means lower peak forces and lower heat loads on the spacecraft. Even so, the deceleration is brutal. The thick Venusian atmosphere slows the probe dramatically. It experiences peak forces of about 32 times Earth's gravity, all concentrated into roughly 3 minutes. Peak heating at the stagnation point reaches about 500 watts per square centimeter. The heat shield, made of advanced carbon-carbon material, the same type used on the Genesis spacecraft, absorbs it all. And then, at about 42 miles, roughly 67 kilometers above the surface. The probe jettisons its heat shield. A mortar fires to deploy a pilot parachute, which in turn pulls out the larger main parachute. And the science begins. This is not a standard nylon parachute. Nylon would dissolve in the sulfuric acid clouds of Venus. DAVINCI uses a disc gap band canopy, roughly 5.8 meters in diameter, made from material that is acid-resistant and 5 times stronger than steel, held in place by heat-resistant Kevlar cables. For the first half hour or so, the probe hangs beneath its parachute, drifting slowly through the thick cloud layer that extends roughly 19 miles deep. This region is critical. It contains gases and chemical compounds that may originate from Venus's lower clouds, from the surface, or even from the subsurface. During this phase, the probe ingests atmospheric gases through its inlets and runs detailed chemical analyses, similar to the kind of work that the Curiosity rover has performed on Mars. It measures wind speed, temperature, and pressure at regular intervals, every 50 feet or so. Then, at about 25 miles, roughly 40 kilometers above the surface, the probe releases the parachute. It enters free fall. But this is not the violent, rapid free fall you might imagine. The atmosphere of Venus is so incredibly thick, so dense, that the probe drifts downward at roughly 25 miles per hour. Dr. Garvin has described this phase as a relatively tranquil fall, like a stone sinking slowly through water. For the next 30 minutes, the probe continues to fall, continues to measure, continues to analyze. As it descends below 6 miles, it enters a zone where the carbon dioxide atmosphere is just 12 times less dense than liquid water. The views are still hazy, still obscured by the thick air, but DAVINCI's specialized cameras begin to identify different rock types on the surface below. And then, at roughly 1.5 kilometers, about a mile above the ground, the view's clear. The mountains of Alfa Regio come into focus beneath the probe. DAVINCI's descent imager captures hundreds of photographs in near-infrared light, building detailed 3-dimensional topography maps with resolution at scales ranging from 100 meters down to finer than 1 meter. These are images comparable to what you would see from an airplane window as it makes its approach to land. Dr. Garvin has marveled at this part of the mission. Clear images of the mountains of Venus, he says, for the very first time. Photographs that scientists will use to compile 3-dimensional maps of Alfa Regio, revealing more detail of Venus's terrain than has ever been possible. They will look for rocks that are typically only formed in the presence of water. They will search for landscape features that tell the story of erosion, of volcanic activity, of forces that shaped this alien surface billions of years ago. The entire descent, from the moment the probe first touches the upper atmosphere to the moment it reaches the surface, takes approximately 1 hour, 60 minutes. And every single second is packed with measurements, images, and chemical analyses that have not been attempted since the Cold War. The DAVINCI probe carries 5 instruments inside its titanium pressure vessel, protected from the extreme and constantly changing environment by high-temperature, multi-layer insulation, layers of advanced ceramic and silica fabrics separated by thin aluminum sheets. This insulation keeps the instruments operational as conditions shift from about -50 degrees Celsius at the top of the clouds to over 450 degrees Celsius near the surface. The first instrument is the Venus Mass Spectrometer, or VMS. Built by NASA's Goddard Space Flight Center, VMS is designed to sample atmospheric gas during the descent and provide comprehensive information about chemical composition. It will perform the first complete in-situ surveys of noble gases and trace gases at Venus, with the capability to discover entirely new gas species that have never been detected in the Venusian atmosphere before. VMS is similar in design to the quadrupole mass spectrometer aboard the Curiosity rover on Mars. The second instrument is the Venus Tunable Laser Spectrometer, or VTLS. Built by NASA's Jet Propulsion Laboratory, This instrument makes extremely precise measurements of targeted trace gases and their isotope ratios. It is specifically designed to address questions about chemical processes occurring in the upper clouds and in the near-surface environment. The isotope measurements from VTLS are particularly crucial because they can reveal the history of water on Venus, from ancient times to the present day. The third is the Venus Atmospheric Structure Investigation, or VASI. Using flight-proven sensors, VASI measures pressure, temperature, and winds throughout the entire descent, from entry to the near surface. It provides the environmental context for all other chemistry measurements and enables reconstruction of the probe's descent trajectory. The fourth is the Venus Descent Imager, known as VENDI. Built by Malin Space Science Systems, VENDI peers through a transparent sapphire window mounted at the bottom of the descent sphere. It captures high-contrast, high-resolution images of the tessera terrain below and maps the three-dimensional topography and rock composition of Alpha Regio at scales not achievable from orbit. And the fifth is a student collaboration experiment called the Venus Oxygen Fugacity Experiment, or VFOX, mounted to the outside of the probe to measure oxygen composition in the deep atmosphere. Together, these instruments form what the mission team calls a flying analytical chemistry laboratory. They will generate several gigabytes of data during the descent, all of which must be transmitted up to the CRIS spacecraft before the probe reaches the surface, since the probe is not required to survive impact. The science goals of DAVINCI are layered and deeply ambitious. They aim to rewrite the textbooks on Venus. First, the mission will investigate the composition of the Venusian atmosphere with a level of precision and detail that no previous mission has come close to achieving. The probe will measure noble gases, chemically inert elements like helium and xenon that maintain stable concentrations over billions of years. Noble gases are the time capsules of planetary science. They do not react with anything. They simply persist. By comparing Venus's noble gas composition with that of Earth and Mars, scientists can begin to understand why three planets, formed from similar starting materials, evolved into such dramatically different worlds. Second, and perhaps most importantly, DAVINCI is looking for clues about water. The probe will measure the ratio of hydrogen isotopes, the fundamental components of water, in the atmosphere. This ratio is one of the most critical measurements in all of planetary science because it can reveal whether liquid water once existed on Venus in the form of oceans or whether Venus had only a steamy early atmosphere that quickly evaporated and dried up. Some models suggest Venus may have had a liquid ocean for 2 or even 3 billion years. That is an enormous span of time, more than enough for life to have potentially evolved. But other models suggest Venus never had stable surface water at all, that intensive volcanism or other processes prevented oceans from ever forming. DAVINCI's isotope measurements may help settle that debate once and for all. Third, the probe will measure sulfur compounds in the lower atmosphere. These compounds could indicate whether Venusian volcanoes are currently active or were active in the recent geological past. Understanding volcanic activity is critical because massive, prolonged volcanism may have been one of the primary triggers for the runaway greenhouse effect that transformed Venus from a potentially mild world into the furnace it is today. Fourth, the descent imagery over Alpha Regio will allow scientists to study the rocks and geological formations of a tessera for the first time at close range. They will look for rock types, such as granites, that on Earth are typically formed only in association with water. They will search for signs of erosion, for evidence of weathering processes, for landscape features that might reveal whether these ancient highlands were shaped by volcanoes, by water and wind, or by forces we have not yet imagined. And fifth, DAVINCI's chemical measurements may shed light on the phosphine question that erupted in 2020. If the probe detects phosphine or other unexpected chemicals in the clouds or lower atmosphere, scientists will need to explain their origin. Whether those chemicals result from geological processes, unknown atmospheric chemistry, or something else entirely, will be a question that only data can answer. Here is something important to understand about DAVINCI. The probe is not designed to land. It does not have landing legs. It does not have a landing system. It is designed to fall, to collect data during that fall, and to transmit that data to the spacecraft overhead. All of the essential science data, every measurement, every image, every chemical analysis, will be gathered and transmitted before the probe reaches the surface. The mission is complete the moment the descent sphere finishes its 1-hour plunge through the atmosphere. But that does not mean the probe simply vanishes when it hits the ground. If the titanium sphere survives the touchdown, which occurs at roughly 25 miles per hour, and if it maintains radio contact with the CRIS spacecraft passing overhead, the probe could potentially continue operating for up to 17 or 18 minutes on the surface. During those precious minutes, it would relay any remaining data acquired in the final few hundred meters of descent and continue collecting chemistry and environmental measurements with its analytical instruments. But after those 17 minutes, the heat takes over. The internal temperature rises beyond what the electronics can tolerate. Radio contact with CRIS is lost as the orbiting spacecraft moves out of range. And the probe goes silent, baking on the surface of the hottest planet in the solar system. So the surface phase is a bonus, a potential gift. But the real mission, the part that everything depends on, is that single hour of descent. There is a broader and increasingly urgent reason why this mission is happening now, and it extends far beyond Venus itself. In recent years, the James Webb Space Telescope, the most powerful such observatory ever built, has begun discovering exoplanets, worlds orbiting distant stars far beyond our solar system. Scientists estimate there are likely over 1 trillion exoplanets in the Milky Way galaxy alone, and many of the smaller, Earth-sized rocky worlds that Webb and other telescopes are identifying may be more similar to Venus than to Earth. They orbit close to their stars. They are bright and reflective. They may have thick atmospheres. Scientists call these worlds exovenuses. But here is the problem. If we want to understand whether those distant planets are habitable, whether they harbor oceans or could support life, we first need to understand the actual Venus that sits right next door to us, as close as 38 million miles away. Dr. Garvin has put it plainly. We have to know our Venus. Venus is like an exoplanet in our own cosmic backyard. Studying it in detail gives us a reference point, a baseline against which we can interpret data from worlds we will never be able to visit in person. If we can understand how and why Venus became what it is, we can better evaluate the nature of the thousands of Venus-like worlds scattered across the galaxy. And there is one more dimension to this, perhaps the most sobering one of all. Understanding what happened to Venus may also tell us something about the possible future of our own planet. Venus may once have been a habitable ocean world, with moderate temperatures and liquid water on its surface. It is not anymore. The evolutionary path it followed, from habitable to hellish, connects to the long-term questions about Earth's own climate and future. As the DAVINCI team has stated, Venus's evolution from a possibly habitable ocean world to its current state, with no oceans at all, is important for us here on Earth, as it connects to various pathways for the long-term evolution of our own habitable home planet. DAVINCI does not stand alone. After decades of neglect, Venus is coming back into the scientific spotlight, and the upcoming wave of missions represents the most ambitious effort to study this planet in human history. Alongside DAVINCI, NASA also selected a mission called Veritas. Veritas will orbit Venus and use advanced radar to map the surface in unprecedented detail, investigating the planet's geological history, searching for evidence of plate tectonics and active volcanism, and studying how Venus's interior processes shaped its surface over billions of years. The European Space Agency is planning a mission called ENVISION, also designed to study Venus from orbit during the 2030s adding another layer of remote sensing data to complement the in-situ measurements from DAVINCI. Together, these three missions form the most comprehensive effort to understand Venus in the entire history of space exploration. And DAVINCI sits at the very center of that effort, because it is the only mission that will actually enter the atmosphere and make direct measurements from within. No previous mission within the Venus atmosphere has measured the chemistry or environments at the level of detail that DAVINCI's probe can achieve. No previous Venus mission has ever descended over the Tessera Highlands. None have conducted descent imaging of the Venus surface. These are firsts across the board. DAVINCI will build on what the Huygens probe accomplished when it descended through the atmosphere of Titan, Saturn's largest moon, and it will improve on what every previous Venus mission achieved, but with 21st century capabilities and sensors. The instruments are more precise. The data transmission system is smarter, using an adaptive data rate that adjusts in real time based on signal-to-noise conditions and atmospheric attenuation. The thermal protection is more advanced than anything available in the 1980s. This is not a repeat of what came before. This is a new chapter in the exploration of our nearest planetary neighbor. As of now, DAVINCI is in development. NASA's Goddard Space Flight Center leads the mission. Lockheed Martin is building the carrier spacecraft in Denver, Colorado. Major partners include the Johns Hopkins University Applied Physics Laboratory, NASA's Jet Propulsion Laboratory, Malin Space Science Systems, NASA's Langley Research Center, NASA's Ames Research Center, Kinetex Incorporated, and the University of Michigan. If all goes according to plan, the spacecraft will launch in 2029. It will spend 2 years performing gravity-assist flybys and remote sensing passes, carefully maneuvering into position. And then, in 2031, at high noon, over the ancient mountains of Alpha Reggio, under ideal sunlight, a 3-foot-wide titanium sphere will be released into the sulfuric acid clouds of Venus. For 1 hour, it will fall. It will taste the atmosphere. It will inhale gases that have not been sampled since the Cold War. It will measure the wind and the pressure and the temperature at every altitude. It will photograph mountains that no human eye has ever seen in detail. It will search for the chemical fingerprints of an ancient ocean that may or may not have existed. And then, it will go silent. But in that single hour, in those 60 minutes of descent through the thickest, hottest, most corrosive atmosphere in the solar system, we may learn more about Venus than we have in the past 4 decades combined. We may learn whether our sister planet once had oceans, whether it once had the conditions necessary for life, whether something in those ancient rocks or lingering gases tells the story of a world that was not always so hostile, a world that might have been, for a time, something beautiful. Or we may discover something entirely unexpected. Something in the chemistry that does not fit any of our models. Something in the clouds that we did not think to look for. Something that rewrites everything we thought we knew. That is the nature of exploration. You build the instrument. You drop it into the unknown. And you see what comes back. For now, Venus keeps its secrets. It hangs in our sky, shrouded in acid clouds, glowing in the early morning like a jewel, beautiful from a distance, terrifying up close. A world that looks like it should have been our twin, but became something else entirely. But not for much longer. As Dr. Garvin has said, we have not seen anything yet. What we know so far is this. Venus is the most Earth-like planet in our solar system by size and composition. And yet, it is among the most hostile worlds we have ever studied. Here is what the data suggests. Something catastrophic happened to Venus billions of years ago, something that transformed a world which may have been habitable into an oven. Some researchers believe liquid oceans persisted on Venus for billions of years. Others argue the planet was never truly hospitable to begin with. What if the answer to what went wrong is locked inside the atmosphere, buried in the chemistry of gases that have not been measured since the last Soviet probe fell silent on the surface? DAVINCI is designed to go and find out. It is not making promises. It is not claiming to have the answers before it arrives. It is asking questions. And sometimes, that is how the most important discoveries begin.